Hello and welcome to a video from the vault, where we peek into a classroom and see what there is to learn. Today we will listen to an introduction on deductive reasoning. Enjoy!
We're continuing, and we're next doing or discussing the friend of inductive reasoning, and that is deductive reasoning. With inductive reasoning, we saw, now we're not using it a lot, but we do want to be aware of what it is, its benefits, and its shortcomings, the danger of using inductive reasoning. We can't be without it, because we can't go and check every single thing out there, or every example that we can come up with. It's just not practical. But it is a scientific and natural way of thinking. Deductive reasoning, on the other hand, says, no, we want to be able to prove beyond any possible doubt that some conclusion is true. And for that we have a series of logical statements, starting from a simple point that everyone agrees with, systematically leading to a conclusion. And if you follow the path of the statements, there is no doubt that the conclusion is correct. So it's different, but more difficult, because we have to come up with a path to get to an answer, and we'll have to figure out how do we do that. So it's more difficult, because you're not just looking at examples and seeing what you can see, but it's also better in the way that you're 100% sure that your conclusion is correct if you built the sequence of statements correctly. As a little example, let's look at a little checkerboard, and we're going to just come up with a little game just to introduce this idea of making a conclusion by way of examples versus making a sound conclusion that everyone agrees is true beyond any doubt. So let's suppose we have two players. Player A can place a token or a coin or something on any two of the squares. And player B then has to place paper clips covering two squares, like those, trying to fill the rest of the board. And if player B is able to do that, then player B will win. If player B is unable to do that, player A will win. So player A really has the choice of placing the two markers wherever they want. They can only place exactly two. And then it's up to player B to see if they can fill the rest of the board with paper clips. Every paper clip covers exactly two, of course, adjacent squares. And if they can do that, then they win, or A loses. And if they can't do it, then A wins. So in this first one, clearly the paper clips cover everything else, so B wins. In the second one, B wins as well. In the third one, there are some squares left that B can't cover with a paper clip. We can't have the paper clip hang over the edge of the board. That won't make any sense. So there's no way to cover this, so A wins. Here, B covered it perfectly, so B wins. Here again, there is a square left, which can't be covered by a paper clip. They can't overlap. They have to be separate, not hanging over the board. So I can't cover a single square, because any paper clip will cover two. So A wins. And in this one, it's perfectly covered again. B wins. Here, there's that square left and the square. So A wins because B wasn't able to fill the whole board. And here A wins again. So now the question is, we can phrase this many ways. Let's focus on A, for example. How do we know for sure, not just looking at those examples, or looking at those examples? Inductive reasoning would help us try and see a link between the situations where A wins and the link between those where B wins, and trying to make some sort of conclusion and hope it works in general. Hope our examples were sufficient. But with just 8 examples, I'm not going to be that confident in any conclusion that I can make. Deductive reasoning says, no, let's look at this without looking at specific examples, but instead coming up with a general argument to decide when A can win and when A will lose. And because of that, it's more difficult to know, well, where do I start? Examples are so easy to make, but a general argument, regardless of the specific examples, that's a little more difficult. So before we look at the sequence of questions that can help us start this deductive reasoning path, just want to make sure what deductive reasoning is trying to say in contrast to inductive reasoning. It's now trying to come up with a method of logical steps to make a conclusion that everyone will agree is true. And there is no doubt that some example would maybe contradict this because it's not based on any example. It's based on a general argument about how the game works. So this is a way to prove that something is true, whether it is just a bunch of English sentences that we'll mainly focus on, or a much more technical looking mathematical proof. The idea of deductive reasoning is the same. So we're trying to prove our eventual conclusion with these statements. So let's, and if it's a fancy conclusion, we can call it a theorem. So let's look at the board again. Let's look at the examples maybe, just so you can remember the game. And in the book, this is exercise 1.4. If I turn the page, those examples are there again, with some questions trying to suggest or lead me to what this could look like. Just to get a feel for it. It's still going to be a little messy, but we'll clean it up a little bit after we read and work through those questions. Let me just reorganize this. Where am I now? I have zooming issues. There we go. All right. Question 1. So I'm not going to write down necessarily in perfect detail, but just enough so that you can make your own notes. Let's look at the squares on which pennies, in this case pennies as the tokens, were placed on each board. Could their colors be related to who wins? Now the difference between deductive and inductive reasoning is that just because those examples lead me to see maybe something, some can see more than others, that just creates suspicion. So if I look at this, what do I see about where the pennies are and when A and B win? Is there anything you can see about the squares that the pennies are on? Any link, anything you see from these limited 8 examples? I think she's first.
B wins when there's one on a black and one on a white.
It seems, well, you're totally right. Or you can say A loses. Later on, I'm going to focus on A, so I just want to phrase it like that, but you're totally right. A loses / B wins. Someone's going to win. When there's a penny on black and, whoops, that does not sound nice. Black and a white square. Does everyone see that? Based on these examples, that is true. But of course, I don't know if that's true in general. Number 2, if you conclude from these 8 examples that your answer to the first question is correct for every possible game, what kind of reasoning are you using? If we're using these examples to make a conclusion about the game in general, what kind of reasoning is that?
Inductive.
Inductive reasoning. And you know, that comes with a little asterisk. Because it depends on our examples. Are they enough? Are they varied enough? So inductive reasoning is not 100%. Number 3, I just answered that question. Do these 8 examples prove what we say in number 1 in general? That A will always lose, B will always win when there's a penny on a black and a white square. Do these examples prove that beyond any doubt?
No.
No, inductive reasoning always has a little doubt, especially with only 8 examples. So how can we have 100% certainty? I don't want to go too fast, but the camera's only focused on this board, so I'm going to have to erase this board a little bit. But I'll do it in this way. So I feel happy with my statement in number 1. It does seem that that is the winning-losing condition for A, but I'm not 100% based on these examples. How can I get to 100% without playing like millions and millions of games? That's not very practical. Deductive reasoning is the way to do that. So number 4, according to the rules, each paperclip has to be placed on 2 squares that share a common side. 2 adjacent squares will be under the paperclip. What can be concluded about the colors of any 2 such squares? If you're looking at the squares underneath a paperclip, or the squares that a paperclip covers, what is always true about them?
The paperclip covers 1 black and 1 white.
1 black and 1 white. Any paperclip that's being put down within the rules of the game, that is always going to be the case. So that's information about how the game works that we might use. 5. If player B is able to place 7 paperclips so that they cover 14 squares, because there's a total of 16, so he's going to have to cover 14 squares. If player B is able to do that, what must be true about the colors of the 14 squares that it covers, or the number? It's going to have to be 7 black and 7 white. They're going to have to be the same, because every time he puts down a paperclip, or she puts down a paperclip, it's ticking off a black and a white. So the number of black squares and the number of white squares under all the paperclips will always have to be the same. Is everyone happy with that one? Let's erase these now. 6. Of the remaining squares, how many squares are there of each color if player A begins by placing the pennies on 2 white squares? So player A goes first. If they place the pennies on 2 white squares, how many black and white squares are left for B to work with?
6 and 8.
6 and 8. What did we say here? So white squares, so 6 white, 8 black. That's the first part to the question. There's a sub-question there. What about 2 black squares? If A puts it on 2 black squares, then it's the other way around. Then I have 8 white and 6 black for B to work with. And what about if A puts it on a white and a black square? Then I'll have 7, 7. Now, I want to go slowly enough because these things aren't obvious and easy to say in a systematic way for everyone. Some people are thinking, this is so simple, why are you making such a big deal of this? Because it's not simple for everyone. And some situations are simpler than others. So, depending on where A puts the pennies, I might not have an equal number. And anything that black works with, anything that black has to work with, if they have any chance of placing or of covering all the squares, they're going to have an equal number. So in these situations, black has no chance of doing it. B has no chance of doing it. So A will win on those, because B cannot possibly do it, because any covering of paper clips have an equal number. And in this one, because we have such a limited board, it's not hard to see that A is going to lose. If B just places it correctly, they can always do it. They just need an equal number. So these questions sort of lead me to now I can go through this process, asking questions, making statements with someone else, and convince them beyond any doubt when A will win and when A will lose. There's no doubt. It's not based on these examples. I use the examples to understand what the game is like, but I don't base any argument on the examples. The argument's done in general. 7, what kind of reasoning are you using? Well, you conclude from your answers to the previous questions, not D and F, that the rule that A wins if, so here, A wins if they place it on the same color. And here, A loses if they place it on different colors. That was the same as our original observation that we thought was true. Now we had some slightly messy argument, but an argument to prove that beyond any doubt. What reasoning are we using now? Now it is deductive reasoning. Is everyone clear on the difference between inductive reasoning and deductive reasoning? Inductive reasoning, we're basing it on specific examples, trying to see a pattern among those examples, making a conclusion in general, not checking other examples. Deductive reasoning, we use examples to understand the game, but nothing in our argument is based on those examples. These are all general statements, never pointing to any specific example. So that when we make a conclusion, we have no doubt that it is correct. Any questions on that? So right now it's all about just understanding the difference in types of arguments. I just want to zoom out here a little bit so we can see both boards. Apparently I can't zoom out any more than that. That's exciting. So now the issue is, well, let's figure out how do we structure, what are these deductive reasoning examples, or not examples, these deductive reasoning steps look like? Well, first of all, we have to just be clear on what a statement is. A statement is a sentence that is either true or false. We say it has a truth value of true or false. Then you ask me, well, wouldn't all sentences be either true or false? Is it necessary to call them something other than a sentence? For example, my pants are black, disregarding the chalk marks on them, mainly black. That is either true or false. One or the other. That is a valid, or that is what we call a statement. Or you can also call it, I guess, a logical statement. Things that you can determine if they're true or false, one or the other. So nice and specific. What about the following? How do you make sense of that? Is it true?
It's a paradox.
Is it false? If it's true, then whatever this says is true, but it says it's false. So if it's false, then the opposite of that is true, meaning the sentence is true. So it's everything and nothing. It contradicts itself. This is not a statement that we are interested in. I can't work with something that isn't either true or false. Self-contradicting. A paradox, if you will. So you can get sentences like that. We can work with sentences like that. Unfortunately, they're always there in any logical system, but they're not really breaking anything. It's just something that we have to be aware of and avoid. They're not really something we can work with. There's a little story that I cannot for the life of me remember where I heard it. Can't remember. Of this Indiana Jones type character in the jungles of South America. And he comes across a statue, a big head with a hole where the mouth is. And he figures out the writing, and it says, whoever puts their hand in this hole and speaks the truth will be able to pull their hand out. But if you put your hand in and you tell a lie, then you'll never be able to take your hand out. So he thinks about it a little bit. He puts his hand in and says, I'll never be able to pull my hand out. What happens? Take a few seconds and think about it. What do you think happened? Any ideas? So if he tells the truth, you'll be able to take his hand out. If he tells a lie, then he can't take his hand out. So he puts in his hand and says, I'll never be able to take my hand out. What do you think happened? Is it true what he said? No, because then he would be able to take his hand out. Right. So it can't be true. Is it false what he said? If he says, I'll never be able to take my hand out. If that's a lie, then you should take his hand out. But if he tells a lie, he can't take his hand out. See, so it's everything and nothing. It makes no sense. I don't know what happened. Maybe the statue blew up. I don't know. So you get weird sentences like that that are fun to think about, but not something we can logically work with in an argument. So what can we work with? What does deductive reasoning look like? Well, the basic form of deductive reasoning, or flow of how you can structure a basic argument, looks like this. There are many examples that you can use, but I like the following one. You have what we call a premise. Then you make some sort of observation. And then you draw your conclusion. Now in the more complicated ones, there could be multiple statements in the observation and in the premise, but we're not going to get that fancy. We're just doing an introduction to see how these things work. The premise is a statement that no one is going to question. We have to have some starting point. Like 1 plus 1 is 2. No one questions that. You have to have something that is true beyond any doubt. You have to have something to work with. So an example would be, if it rains, then the grass is wet. Now don't worry about tenses or grammar too much. I'm just picking whatever is convenient to make it as clear as possible. You can always phrase it in a more proper way. If it rains, then the grass is going to be wet. No one is questioning that. It's a fact. Now I look outside and I see, let's say it like this, today it's raining. Or today it rained, or whatever version of the sentence you want. What is my conclusion then, using the premise? Anyone at all? The grass is right. I didn't say it was hard. That is the basic structure of a deductive reasoning argument. See, it's not hard at all. Not hard at all. Let me just check here. We can do it this way. There is also slightly an alternative one, which is exactly the same, but the phrasing is a little different in appearance. We can also say it this way. We still have premise, observation, and we make a conclusion. Premise is the same. If it rains, then the grass is or will be or can be wet, however you want to phrase it. Now you go outside and you look at the grass and you see that the grass is not wet. What do you conclude beyond any doubt? It couldn't have rained. However you want to say it, it is not, rain. Because if it rained, the grass would be wet. You're looking outside, you see dry grass, meaning it cannot be raining. These are the same. They look maybe a little different, but they're both equivalent deductive reasoning examples. Any questions on this basic structure of deductive reasoning? Does it make sense? You can use your own example. I like the rain and the grass one. Probably one of the ones I heard of first. But it makes sense. It feels very natural, really. We're just giving it some structure, but breaking it up into a few steps. So before we do that, let's go back to my game of placing pennies and paper clips. And now let's see, how can we use this structure of deductive reasoning to have maybe a clearer argument to prove when A is going to win and when A is going to lose. So we could say, how do I want to say it? I want to say it exactly right. How do I say it in the book? Let's say it like this. If A loses, And I'll say here that means that B can cover the remaining board or remaining squares with paper clips. Those two things are the same, right? A losing means B was able to cover the remaining squares. B covering the remaining squares, A loses. Those two things are the same. Doesn't matter which one I use. The book uses the B one, I'll use the A one, doesn't matter. These two things are the same. If B is able to do that, then what did I say about the number of black and white squares? Then let's say there was an equal number of black and white squares, let's just say left, because I don't have a lot of space to fit in remaining. So that has to be, the premise has to be a statement that no one is questioning. Probably should have turned the camera, that would have been a wise choice. So, is there anyone that questions the premise? It has to be a simple enough statement that no one questions. Like, if it rains, the grass is wet. No one's going to question that. It's a general statement. I'm not looking for little technicalities. So, I'm saying a similar type, I'm making a similar type of statement, an if-then sentence, to match it with my simple example. If B can cover everything, then there was an equal number of black and white squares. Based on the rules of the game, that is the only way he can possibly cover everything that is open. Now I make an observation, like, depending on what player A does, player A places the pennies on two squares of the same color. But suppose that's what happened. Does it match that alternative form of the rain and grass example? So I'm now, the observation that I make is the opposite of the then section in the premise. Like here with the rain and the grass, it was if it rains, the grass is wet. I observe the opposite of the second part of the premise. The same thing is happening now. That if B can cover everything that remains, there's an equal number of black and white squares. I now observe that A places pennies on the same color, so there isn't an equal number of black and white squares. Let's squeeze it in here, actually. Because the observation could be multiple things, multiple sentences, depending on the complexity of the argument. So, there isn't an equal number of black and white squares left. We have the time. I want us to think about what we're doing and ask if something's not clear, not just copy what I'm writing down. I already did that for you in the book. It's all there. But rather, let's try and keep up with what's happening and try and understand, and then you're solidifying that when you look in the book again. So my conclusion is then, well, what happened with the rain and the grass example, if I observe the opposite of the second part of the premise, I conclude that the first part could not have happened. Otherwise, I would have the second part. So I conclude the opposite of the first, which is, let's go for a therefore. Therefore with an E or not? I don't know. You want an E? Depends on where you're from, I guess. Therefore A wins. Therefore B cannot cover everything, so A is going to win. See the similarity. Take a simple example to figure out the structure of the deductive reasoning process, and then when it gets more complicated, you're trying to match it with what you're comfortable with and see how you can structure it in the same way. Now I will say, in case there are people thinking, well, how am I going to come up with this on my own? Right now we are doing an introduction which just gets me familiar with these concepts. We can't really use them because they are difficult. Later on, we'll have logical arguments like this, but for now, it's going to be difficult to structure them exactly like this. But every now and then it'll come up. So we want to, at the very least, be aware of what is the difference between inductive reasoning and deductive reasoning. They look very different. Inductive reasoning has a few examples, and I see, hopefully, the correct conclusion. It's a little hit and miss, depends on my examples. Deductive reasoning has none of that and gives a general argument that gets me to the conclusion without any doubt. They're very different. Both have their place. Pros and cons for each. What is the pro of the inductive reasoning? What do you think is a positive thing that it has going for it?
It's quick.
It's quick. Making examples are easy. The negative, we've discussed that many times, but I'm really just testing if you've been paying attention. What is the negative side of inductive reasoning?
Just can't be sure.
Can't be 100% sure, really ever, because if there are more examples that I haven't tested, I can't be 100% sure. On the other side, deductive reasoning has pros and cons as well. What is a pro?
Guaranteed.
Guaranteed, 100%. If I structure this correctly and clearly, the conclusion is 100%. What is a con, would you say? Where examples were easy to make, deductive reasoning would not be so easy to come up with. And that's why we're not really taking this and running very far with it. I do want to, are there any questions before we continue? I'm so sleepy and tired. Too much? I didn't put any equations or numbers on there. Isn't that a good thing? But it's still mathematical thinking. Mathematical thinking is really just logical thinking. And if we don't understand the kinds of logical thinking, then putting numbers and variables and equations on top of it makes absolutely doesn't make it better at all. So I want to be aware of how we're thinking first. What are the limitations of how we're thinking? Pros and cons for different types of reasoning. Any questions at all? We have a lot of time. You can ask questions, comments, concerns, criticisms. If you like this, feel free to say it. If you don't like it at all, you can say that too. It's not going to change, but you can still say it. It makes you feel better. We have to look or mention the following. Variation on this. Premise, observation, and conclusion. Did I call it an observation in the book? I can't remember. Yes.
Yeah.
Premise, I'm going to stick to the rain one because I feel comfortable with it. If it rains, then the grass is wet. Now you look outside and you see the grass is wet. And you make the conclusion, I'll say it like this, that's you, it must have rained. Does it fall under inductive reasoning or deductive reasoning? Is it based on any examples that I list and try and look for a pattern? No, I didn't make any examples. It's trying to be inductive reasoning. Is it sound inductive? Is it sound deductive reasoning? No. Why not? I wrote premise, observation, everything.
Maybe let it
Grass could be wet from something else.
Yes, the grass could have been wet from something else. Sprinkler. Someone spilled water, I don't know, something. It doesn't have to be that it rained. So this is now not 100%. Now I'm just going to write the other common one over here. It rains, the grass is wet. The correct one was today it rained, and therefore the grass is wet. That was the original, and everyone agreed with that one. Now this one is moving things around, and now it's not 100% anymore. What is the difference between the two? Where is the difference? Where's the first difference? You're very chatty. I can't even say anything.
The other one's just an assumption.
You need to chat more and talk. Because I don't know if you understand anything if you don't give me feedback.
The reverse.
Don't be afraid to say what you want to say.
One says it's today, and one says
Well,
it doesn't.
all right, fine. You got me on a technicality.
Observation and conclusion are reversed. Like one
In the observation, I'm taking different parts of the original premise. In the original correct one, I observed the first part of the premise and then concluded correctly the second part. Because the premise said whenever it rains, the grass is going to be wet. So if it rains, the grass is wet. This one takes the second part and concludes the first, which is a likely possibility, but it concludes it as if it's fact. This only goes one way. It doesn't say the other way. It doesn't say if the grass is wet, then it rains. It only says if it rains, then the grass is wet. It doesn't go the other way. But this is essentially assuming that it does, which it might not. It might not. So this is not sound deductive reasoning, but it happens so much that we give it a name. Can't remember where the name comes from. It's called abductive reasoning. Maybe you're abducting part of the premise. I don't know. Sure, it comes from something. Abductive reasoning. Where you're taking the second part of the premise and concluding the first, the likely possibility, as if it was fact. Which doesn't necessarily, isn't necessarily going to be the truth. And if you think about this a little bit, this is what the Sherlock Holmes character really does. He doesn't use sound logical reasoning. He uses inductive reasoning, where you make observations, collect evidence, or whatever the story may be, and then exhaust enough possibilities so that the one that's left, however unlikely, is probably the correct one. But it's not a guarantee that it's correct until the criminal confesses or something. Doesn't necessarily mean it's correct. So I have to be aware of this so that I don't fall into that trap, and I can spot it when someone else does it. Maybe in your classroom one day, if you're aiming to be a teacher, you'll see little Timmy do exactly abductive reasoning when he does something like this. If I, as the student, if I answer my test question correctly, turn the camera here. Do we have time? Yeah, lots of time. Rolling in time. If I answer my test question correctly, then I will get the correct final answer. Everyone's going to agree with that. That is definitely a fact. If I answer the question correctly, I'm going to get the right answer. No one's questioning it. Now little Timmy comes to you and says, "Teacher, but I got the right answer." Or correct final answer. Therefore, why am I not getting all my marks? Because obviously then I did the question correctly. And I should get all my marks. But what form of reasoning is this? That's abductive reasoning, which is not a sound form of logical reasoning. Just because you get the final answer right doesn't mean you did everything correctly. You might have made a couple of mistakes and just happened to get the right number in the end. Doesn't mean it was correct. For example, if I have to calculate something like, I think it's this. What is the answer to that? What is the answer? Well, the numerator is a 4, so we know it's a 4 over 8, which is a half. It's a little early for fractions. Yes, fractions only come in part 4, but nonetheless. Timmy says, there was something about common factors, where if I see the same number on both sides of the line, I can cancel them. I'm going to do that. And then I get 2 over 4, which is also a half. I get the right answer. Didn't I do it right? No, I didn't do it right. I can't cancel those. So just because you get the right answer, Timmy, doesn't mean you did the question correctly, or you know how to do it. Abductive reasoning. The type of reasoning that people use most of the time. It is not 100% that your conclusion is correct. Likely, but not necessarily correct. And we have to be aware of it, and then you'll start to see it in how people speak and reason. And you'll see that it's full of flaws all the time. All the time. It's not logically sound reasoning.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Also, please visit me on my Patreon page if you want to support me in making further content. Thank you.